Okay. So we were discussing about Lebesgue integral, a hierarchy of definitions to handle integral of a measurable function. I think it's better to recall the progress, how to make this integral progressively better and better. At the ground level or elementary level, Lebesgue dealt with simple functions. As you know, simple functions are extensions of step functions. Basically, simple functions are those whose range set is finite. The function takes only finitely many distinct values. I called it as level 0. Let phi from R to R be a simple function. As per our definition, a very simple function is measurable. And let us say phi can be written as summation I is equal to 1 to n alpha I chi ei. You can always write a simple function in this form. Perhaps in the canonical form or in a form like this where we don't require alpha 1, alpha 2, etc., alpha n to be distinct and E1, E2, E3, etc., En to be disjoint. We don't require that. But in canonical form, alpha i's are distinct. Ei's are sets over which function takes the value alpha I and ei's are disjoint. Whatever be the way in which you are writing, we can define integral of phi as integral over R phi dm. I am using dm in order to reveal that we are handling Lebesgue integral, not the Riemann integral. Is equal to summation I is equal to 1 to n, the values taken by the function times quantification of the sets over which those values are taken. And if you want to handle integral over a measurable set, not necessarily R, then we can handle in variety of ways. One easiest way to handle this is the following. Integral over E phi dm is equal to integral over R chi E, characteristic function on E, times F dm. Because characteristic function switch on only on E and it is switched off outside E. So in effect, you are integrating only over E. So this is the level 0. And in level 0, you have observed that integral over E or R, whatever it is, A phi dm is equal to 8 times integral over F dm. Okay. And in fact, to avoid the problems like infinity minus infinity and so on, we can take phi to be a non-negative simple measurable function. non-negative, where a is greater than 0. And also you have integral over e phi plus psi dm is equal to integral over phi dm plus integral over psi dm. And of course, there are few more properties, but linearity is what I want to highlight. Okay. So this finishes the ground level. With this in hand, we went to slightly better level, where we handled any measurable function which is bounded and defined on a set of finite measure. Let f be a bounded measurable function defined on a measurable set E with a finite measure then we define here we are mimicking the Riemann integration theory. Lower Lebesgue integral of f over E to be what we know is only to integrate. At this point, we know only to integrate simple function. So you, instead of integrating simple function, you integrate the, sorry, instead of integrating the given function, you integrate a simple function, okay, where phi is less than or equal to f, phi simple. So this is an underestimate. Make them better by taking infimum. Or
Supremum.
because you are underestimating, it should better and better. You should take supremum. You are right. Thank you. And similarly, you can define upper Lebesgue integral. You integrate, instead of given function, you integrate simple function, where that simple function is greater than or equal to f. So you are overestimating it, make it better and better. At this point, and or in this level, we say a function is integrable. We say f is integrable. You should keep in mind that integrability varies in each level. The meaning of integrability. Here, a function is said to be integrable if lower Lebesgue integral coincides with upper Lebesgue integral. And we know that this is possible if and only if f is measurable. And that's why we started with a right assumption that f is measurable. Okay. So having defined integral for a bounded measurable function, at that point, again, we wanted to see whether it satisfies all the linearity property and so on. Okay. So note that in this level also, integral over E AF plus BG dm is equal to integral of A times integral over E f dm plus b times integral over E g dm. So, but I want to do make a clarification here. We have proved this in detail. Okay. If you go through the proof, first we prove the scaling property. Integral of a f dm is equal to 8 times integral. We observed first that integral over e a f dm is equal to 8 times integral over e f dm. And again, to do that, we split it into two cases, a greater than 0 and a less than 0. And the crux of the matter lies in the fact that whenever phi is simple, 8 times phi is simple, and conversely, assuming a non-zero. Okay. The crux of the matter is the observation that phi is simple if and only if a phi is simple, a not equal to 0. And using this, we split the proof into two cases, a greater than 0 and a less than 0. But while writing the detail for a less than 0, we have made a mistake. Thanks to one student, I forgot his name, who emailed me. So let me clarify that. Let us consider a less than 0. Let a less than 0. So what you want to do is you have to integrate AF dm. Okay. By definition, this is equal to either you can integrate the simple functions less than AF, or you can integrate simple functions greater than AF and then make that estimates better and better. So let us take infimum of integral over all psi bar dm, where psi bar is greater than or equal to AF, psi bar simple. Do you agree?
Yes, sir.
Yes. Integrating AF, we will achieve via integrating a simple function, greater than or equal to AF. Or you could have done less than or equal to AF and then take supremum. Okay. Now, varying over all simple function greater than or equal to AF is same as varying over all simple function psi bar by A less than or equal to AF, because A is less than 0. So psi bar greater than or equal to AF will give you psi bar by A less than or equal to AF. Okay, so let me note down that varying over all simple functions psi bar greater than or equal to AF. If psi bar is simple, psi bar by A is simple. There is no doubt about it. But inequality will get reversed. Okay. Is same as varying over all simple functions psi bar by A less than or equal to F. That is over all simple functions phi less than or equal to F. So I can write the infimum that we are interested as equal to infimum over all phi less than or equal to F, phi simple, integral over E. Okay, psi bar will be A phi dm. Okay. Now, while pulling A out, the infimum will turn to supremum because A is negative. That part we missed. Okay. So this is equal to A times supremum phi less than or equal to F, phi simple integral over E phi dm. Do you agree? This is what we missed in the last lecture. Do you agree or not?
Yes.
Because why this infimum and supremum got interchanged?
Because sir, A is negative.
A is negative. Now this is equal to 8 times. Now use the fact that phi is a non-negative simple function or whatever it is. Okay. I don't think non-negative is needed. But supremum over this, if f is measurable, we have proved that supremum of this is same as infimum psi greater than or equal to f, psi simple integral over E psi dm. That we have proved. F is measurable, then lower Lebesgue integral is equal to upper Lebesgue integral. And this is equal to 8 times. This is actually integral over E f dm. So a small part we have overlooked. So this should be the right proof. Okay. Thanks to that student. Okay. So that finishes the levels 1. Now in level 2, what we did is, instead of putting the condition that f should be bounded, we avoided the boundedness of f, but compensated it with non-negativeness of f. Let f be a non-negative measurable function over R or over any measurable subset of R defined on a measurable set E. I don't require measure to be finite. Then we define integral over f dm is equal to, right now we can integrate any bounded measurable function. Therefore, to define integral over E f dm, we will seek help of any bounded measurable function. Integral over E h dm, h is less than or equal to f, h is bounded measurable, and then take supremum. But we know only to integrate over a set of finite measure. So we have to take care of that. Where measure of set of all x such that h of x not equal to 0 is finite. Okay. So this is how we defined the integrability of a non-negative measurable function. Please keep in mind that the integral can be finite or infinite. Okay. If integral over E f dm is finite, we say f is integrable. So at least apparently integrability in level 1 is different from integrability of level 2. We say that a bounded measurable function is integrable if upper Lebesgue integral coincides with lower Lebesgue integral. That is for a bounded measurable function. For a non-negative measurable function, we say it is integrable if the integral value is finite. Okay. And here also we noted that integral over E Cf dm is equal to C times integral over E f dm for all C greater than 0 and integral over E f plus G dm. E could be of infinite measure. Integral over E f dm and f and G could be unbounded potentially G dm. Okay. Once we have this, we can go for any function, not necessarily non-negative. And that was our last stage, level 3. Let f be a measurable function. We define positive part of f plus, f namely f plus, maximum of fx comma 0 for each x. And we define negative part of f by taking minimum of maximum of. So how did I define it? I am always getting confused there. How did I define?
Minus fx comma 0.
Minimum, right?
Maximum.
Maximum. I want to be non-negative again. Please keep in mind. Okay. Now f, you can write it as f plus minus f minus. If integral over E f plus dm is less than infinity and integral over E f minus dm is also less than infinity, then we say f is integrable. Then we say f is integrable. So apparently integrability condition is different in this level. If is integrable. And once it is integrable, we define the integral value as and we define integral over E. This was our last observations in the previous lecture. F dm is equal to integral over E f plus dm minus integral over E f minus dm. We shall move on with this definition, but before that, let me make a comment. Namely, this level 1 we included only to see how it closely mimics the Riemann integration idea. But actually, level 1 can be avoided. You can first define integral for a simple function, and then you can directly define integral over a non-negative measurable function. Integral of a non-negative measurable function without worrying about whether the function is bounded and the set over which you are integrating is of finite measure. So level 1 is actually not needed. Okay, so let me make that as a remark. In the previous hierarchy of definitions, of definitions of Lebesgue integral, one may avoid level 1 and build integration theory as follows. As I told you, level 1 I included only for giving you a feel that the Lebesgue integration exactly mimics what happens in Riemann. Okay. Now, the question is, how do you avoid level 1? Level 0 we have, that is for simple function. So, level 0 for phi simple, phi equal to summation alpha I chi ei. Maybe you can put non-negative as well, non-negative, simple non-negative. Integral over phi dm is equal to summation alpha I measure of ei. Okay. Now directly I am going to level 2. Level 2 for a non-negative measurable function f, we define integral over f dm equal to, can you guess? Right now I know only how to integrate simple function. I avoided level 1. So I don't know how to integrate the functions that are bounded and so on. So in that case, what will be a natural definition of integral over EF dm? Is that difficult, the question is? Forget about the answer. Are you getting what my remark hints to? If you see some other textbooks, you may not see how to handle a bounded measurable function. First, they will talk about simple function. Then they directly talk about non-negative measurable function without bothering whether it is bounded or not. That means they may not handle bounded measurability, Lebesgue integrable in from lower, upper, etc. They may not handle it. In that case, you should not be confused. That's why I am putting as a remark that level 1 can be avoided. Now, how to avoid it? Once you want to avoid level 1, you have only level 0 in hand. That means you can integrate only simple functions. Now I want to integrate a non-negative measurable function. How do you do that?
Approximate f by a simple function.
So that means you integrate over E phi dm, right? Phi is less than or equal to
F.
F. Phi is simple. And then take
Supremum.
supremum. That's it. Here we will not go for psi greater than or equal to F. Psi greater than or equal to. We will not go for. Okay. This is the definition. And once you have for non-negative measurable function, then level 3 you can do. F you can decompose into 2, F plus and F minus, and then you can integrate. So my remark is that the level 1 is not really essential. Then if you ask, why do you include it? Because I wanted to compare it with the Riemann, and you can see that in case of bounded function, our procedure is just mimicking the Riemann idea. For that only I included level 1. Is that okay?
Yes.
So let us forget this remark and then go back to level 3. That means now you are integrating any measurable function, need not be non-negative, any measurable function. What do? You decompose it into 2, F plus and F minus. Both are fortunately non-negative, and you know how to integrate non-negative function either via simple functions or via bounded measurable functions. But that means either by including level 1 or by excluding level 1, you can integrate non-negative measurable functions. Okay. So now with the 3 in hand, we are proceeding. Let me start with a remark. This remark is about definition 3. That means how to handle Lebesgue integral of any measurable function. Need not be non-negative. To handle Lebesgue integrability, first we have to define what is integrability. Lebesgue integral, we have to first define integrability. And we define integrability using f plus and f minus. If both of them are finite integral, then we say f is integrable. Okay, but that is same as f is integrable if and only if integral over E f plus dm is less than infinity and integral over E f minus dm is also less than infinity. This was our definition. And once both are finite, you can define integral over EF as difference of integral over f plus and integral over f minus. That we have done. Now what I want to say is the following. Please keep in mind what was mod f in terms of f plus and f minus. Note that mod f was f plus f minus. Okay. And keep in mind that f plus, f minus, mod f are all non-negative. Okay. Therefore, f plus is less than or equal to mod f. The negative part of f, that namely f minus, is also less than or equal to mod f. And f and g are non-negative measurable function, and f is less than or equal to g. You can easily see that integral over f is less than or equal to integral over g by using simple functions. Is that clear?
Yes, sir.
F is less than or equal to g. F and g both are non-negative. Then integral over f will be less than or equal to integral over g. Therefore, integral over f plus will be less than or equal to integral over mod f. And integral over f minus also will be less than or equal to integral over mod f. So, if integral over mod f is less than infinity, hence, if integral over E mod f dm is less than infinity, what can you conclude?
Integral over E
F plus is finite and integral over f minus is finite. But that is the definition for integrability of
F.
f. Thus, if integral over E mod f dm is less than infinity, then we have f integrable. Conversely, suppose f is integrable, then what is the definition? Integral over E f plus dm is less than infinity and integral over f minus dm is less than infinity. Once both f plus and f minus integral is less than infinity, do you see that integral over E mod of dm will be less than infinity?
Yes.
Conversely, if f is integrable, then integral over E f plus dm is less than plus infinity and integral over E f minus dm is less than plus infinity, and that will imply integral over E mod f dm is less than plus infinity. Now, for a non-negative function, how did you define integrability? What was the definition of integrability for a non-negative function? Level 2. A non-negative function is Lebesgue integrable if integral value is finite. So integral over E mod of dm is less than infinity gives you what?
Mod f is integrable.
Mod f is integrable. So essentially, what did I prove through this remark? Who can conclude what is this remark says?
F is integrable if and only if mod f is integrable.
That's it. Thus, f is integrable if and only if mod f is integrable. Lebesgue integrable. But you should be careful. Integrability of a non-negative function we define as integral is a finite value. Whereas integrability of a general function we defined as integral of both positive part and negative part are finite. Okay. So the word integrability have apparently different meaning for a non-negative function and for a general function. Whatever it is, we have proved that a function is integrable if and only if its modulus is integrable in the Lebesgue sense. Is it true in Riemann sense? A function is Riemann integrable if and only if its modulus is Riemann integrable?
No, sir.
That's not correct. For instance, you can talk with Dirichlet functions. You can work with Dirichlet functions. F of x is equal to 1 when x is rational and minus 1 when x is irrational over 0, 1. If you take, it is not integrable. Whereas mod f is a constant function which is integrable in the Riemann sense. Okay. In the Riemann sense, integrability is via upper integral, lower integral, etc. In Lebesgue sense, integrability depends on the context, whether it is non-negative, whether it is a general function, etc., etc. For a non-negative function, integrability just means that integral value is finite. For a general function, integrability means that the positive part and negative part are integrable. Is that clear?
Yes, sir.
Yes, sir.
So only this remark we have done something new today. F is integrable if and only if mod f is integrable. Okay. Now second remark regarding definition level 3. That means regarding definition of a integrability or integral of any function, any measurable function. If you closely observe, integral of f depends upon the decomposition. First, you decomposed f into two, f plus and f minus, and then you define integrability of f via integrability of f plus and integrability of f minus. And once it is integrable, you define integral of f via integral of f plus and integral of f minus. That's what we have done. So one may feel that all this integrability, integral, etc. depends on how you decompose f plus and f minus. But actually, it is independent of the decomposition. That's what I am going to say next. Suppose we have two different decomposition of f into difference of non-negative functions. Say f you have written using your peculiar functions, typical functions, f plus and f minus. And you could arbitrarily write f as difference of two non-negative functions. Let us say g minus h. Okay. Where g comma h are non-negative. It may appear that to define integral of f, you should employ only f plus and f minus. You should not employ arbitrary decomposition of into non-negative function. It appears like that, but actually either you can go via f plus minus f minus, or you can go via g minus h. How? Let me illustrate. Is that clear what we are doing next? Yes or no?
Yes, sir.
Please remember, given f, the decomposition as f plus and f minus is unique, because f plus is defined in a peculiar way. F minus is defined in using maximum, etc. So they are defined in a peculiar way. Therefore, once f is fixed, f plus and f minus is fixed, and f plus minus f minus is unique. But possibly you can write same f as difference of two other non-negative function. Let us say g minus h. Okay. Then do you see this? F plus h is equal to g plus f minus. Remember, f plus, f minus, g, h are non-negative. Okay. Now these are two non-negative functions. They are equal. Therefore, integral will be equal. Therefore, integral f plus h dm is equal to integral g plus f minus dm. By linearity of integral of non-negative function. By the linearity of integral of non-negative function. Is that okay?
Yes.
Now suppose f is integrable, then this f plus, f minus all are having finite value. So you can write this integral over e f plus dm minus integral over e f minus dm is equal to integral over e g dm minus integral over e h dm. Okay, and what you have in the left side is what you have in the left
Integration
side
of
is
f.
integral over e f dm by definition, right? But that is same as integral over e g dm minus integral over e h dm. What was g minus h? A decomposition of f into two non-negative function. So to define integral over e f dm, you could very well employ g minus h as well. Do you get my point? That is, value of the integral is independent of which decomposition you are using. Decomposition into two non-negative function. Is that clear?
Yes.
That is,
Yes, sir.
value of the integral. This important observation we will use. Value of the integral of f is independent, provided it is integrable, okay? Independent of the decomposition. We shall use standard way f plus and f minus, but if you can do it in a different way, f you could write as difference of two non-negative function by inspection itself, then you can define integral of f by using that decomposition. You don't have to always employ f plus and f minus. Okay. So these are two remarks regarding the definition of level 3. Now, as in the other level, we have the following proposition, which suggests that integral is linear. Let f comma g be integrable over e Then 1. CF is integrable. Only after verifying it is integrable, you should attempt to write integral. Integral CF dm is equal to C times integral F dm. Okay. Similarly, F plus G is integrable. Now, just to recall, what is the meaning of F plus G is integrable? What is
Positive
the
part of
meaning
F
of
plus
F
G,
plus G is integrable?
positive part of F plus G and negative part of sorry, positive.
Correct.
Both
F
are
plus G, you are right. F plus G plus and F plus G minus are integrable.
integrable.
Are integrable. Or you can say mod F plus G is
Integrable.
integrable. Mod F plus G is integrable. Okay. So F plus G is integrable, and once it is integrable, now you can talk about its integral. Integral of F plus G dm is equal to integral over E F dm plus integral over E G dm. Okay, so linearity is there also for this stage. That's why. Proof. Of course, we shall use the linearity that we proved in the other levels here. Okay. Note that. Proof is simple, so I will keep on writing. If you have some issue, please let me know. Note that F plus G, it is self-explainable each step. F plus G is F plus F plus minus F minus. That is F plus G plus minus G minus. But F plus G has a decomposition. F plus GF plus minus F plus G minus. That is the decomposition of F plus G. But that is equal to F plus minus F minus plus G plus minus G minus. Okay. That implies F plus G positive part plus F negative part plus G negative part. But remember, all these things are positive, is equal to F plus G minus plus F plus G plus. I segregated on the both side the non-negative function without any negative sign. Okay. Now you have two functions. Let us say h1 equal to h2, and h1 and h2 are non-negative. Once they are equal, their integral is equal. Okay. That implies, that follows from the definition. Integral over E F plus G plus F minus plus G minus dm is equal to integral over E F plus G minus plus F plus G plus dm. But now you have on the left side and right side non-negative function, and linearity for non-negative function you already proved. Okay, by a result, by the linearity result, we proved for non-negative function we have, so you can split the integral on the left side and the right side to several integrals. We have integral over E F plus G plus dm plus integral over E F minus dm plus integral over E G minus dm, that is on the left side, equal to integral over E f plus g minus dm plus integral over E f plus dm plus integral over E g plus dm. So far so good.
Yes, sir.
I have just used linearity, which we proved for non-negative functions, linearity of the integral. Now we know all these things are integrable, no? So that you can transpose to the other side and so on. So integral over E f plus g plus minus integral over E f plus g minus dm. There is no issue of infinity minus infinity, etc. Equal to integral over E f plus dm minus integral over E f minus dm plus integral over E g plus dm minus integral over E g minus dm. Okay. And what you have in the left side is, by definition, integral over E f plus g dm. That is integral over E f plus g dm equal to integral over E f dm plus integral over E g dm. Okay. Now, similarly, you can prove for, I will just start, you can, next we prove, next to prove integral over CF dm is equal to C times integral over E f dm. We want to convert this into what we proved for non-negative function. But for non-negative function, you can take only C to be positive. C greater than 0 only we proved. Okay. So what you do is the following. You write C times F as C also you decompose C plus minus C minus. Remember, F plus and F minus etc. are defined point wise. F plus of X, F minus of X. So C plus and C minus for a real number, you can define similarly maximum of C comma 0, whatever it is. Okay. So C plus and C minus you can define times F plus minus F minus. This is for function. Okay. Now this can be written as C plus F plus C minus F minus C minus F plus, I'm just distributing it, plus C plus F minus. Okay. That is CF. But CF has a decomposition, CF plus and CF minus. Therefore, CF plus minus CF minus, that's the decomposition for CF, is equal to C plus F plus C minus F minus C minus F plus C plus F minus. Now what you can do is you can make everything to one side, positive thing. You can avoid negative, so that now you will have two non-negative function and then you can integrate and so on. Okay, and then apply the linearity of non-negative integrals. Okay, now proceed. I will not write all the details. But before that, let me ask one question. Can we avoid this transposition to one side and making everything positive without negative sign? And just from this, can I write integral of left hand side is equal to integral of right hand side? Can I write? Is the question clear first?
Yes, sir.
One thing you can do next is CF plus the minus sign of the right hand side, you can transpose to left. So CF plus c minus f plus c plus f minus equal to so on. That minus sign I can avoid so that you can have left side also some non-negative function, right side also non-negative function, everything with the plus, and then you can take integral on both sides. F equal to g implies integral of f is equal to integral over g. That, and then you can proceed. My question is, can you avoid that step and now itself you say integral of left side equal to integral of right side? Can I say it? Please see the remark that I have given. This remark. Suppose we have two different decomposition of f into difference of two non-negative function, then integral is independent of the decomposition. Yes or no?
Yes, sir.
Yes.
So I can write integral of f plus minus f minus as integral of g minus h. Am I right?
Yes, sir.
Yes.
So here you can write integral of cf plus minus cf minus is equal to integral on the right side. But then can I split it into two integral? There you will have an issue because linearity we proved only for positive functions with
Non-negative.
c greater than 0. Okay. Anyway, I don't want to confuse too much, but this is not confusion. I am giving you too much of simple things which may help, but sometimes it may confuse you also. So let me not do that. Anyway, so you can proceed like this. Next proposition regarding the third level integration. That means most general integration. We proved the linearity. Next. Expected result. If f equal to 0, then what will be integral of f?
0.
0.
But for integral to be 0, you don't want f to be 0 everywhere. It is enough to have almost everywhere. If f equal to 0 almost everywhere, then integral of f dm is equal to 0. Intuitively, can you see why integral will not be affected if you change the function to some other function? Almost everywhere, if two functions are equal, the integral will be same. Almost everywhere, if two functions are equal, then the integral will be same. That's what this proposition ultimately tells you. Do you see the reason? What do you mean by almost everywhere?
Pre-image of dot dead points are pre-image of dead points which measure 0.
Why pre-images? F equal to 0 almost everywhere means were f not equal to 0. You consider all those x for which fx is not equal to 0. Let me remind you the definition of almost everywhere. That is, if you consider set of all x for which f of x is not 0, measure of this set will be equal to
0.
0. This is the definition. Okay. And you know, finally, everything boils down to integral of simple function. Do you agree?
Yes, sir.
And integral of simple function is via summation alpha I times measure of
EI.
EI. So if measure of EI is 0, there is no contribution. Yes or no? If measure of E is 0, there is no contribution to the integral. Do you agree?
Yes, sir.
That's why once f is 0 almost everywhere, whether it is 0 or non-zero at the rest of the point, we don't mind. Finally, the integral will be 0. Do you see it intuitively? The simple reason is that integral is finally boiled down to integral of simple function, and integral of simple function is via alpha I times measure of that. But if measure is 0, then there will not be any contribution. That is why For integral to be 0, the function need not be 0 everywhere. It is enough to have f is equal to 0 almost everywhere. Meaning wherever it is non-zero, we don't bother, but its measure should be 0. Is that clear?
Yes, sir.
Because of the same reason, you should be able to say that if f equal to g, definitely integral of f will be equal to integral of g, no doubt. However, for integral of f to be equal to integral of g, you don't want f equal to g. You want only, can you complete?
F equal to G almost everywhere.
Almost everywhere. F equal to g almost everywhere, you will get integral of f equal to integral of g. Okay. Anyway, so let us prove this proposition. F equal to 0 almost everywhere will give you that f plus is 0 almost everywhere and f minus is 0 almost everywhere. F equal to 0 almost everywhere implies f plus is equal to 0 almost everywhere. F minus is equal to 0 almost everywhere. Okay. Now for a non-negative function, I don't know whether I have proved it or not. If I have not proved it, you can do it as an exercise. For a non-negative measurable function, f equal to 0 almost everywhere implies, maybe I will put a different name. For a non-negative measurable function g equal to 0 almost everywhere implies integral of g dm is equal to 0. I don't know whether I have proved this. Did I?
No, sir.
Doesn't matter. You can prove it your own. Okay. Maybe I will prove it now itself. In fact, it is if and only if. For a non-negative measurable function g equal to 0 almost everywhere if and only if integral is equal to 0. You know that in Riemann integral, if function is 0, integral is 0. If the integral is 0, the function need not be 0. But if the integral is 0 and the function is non-negative, if integral is 0 and the function is non-negative, what can you say? And the function is continuous. And the function is continuous. Can you say the function will be 0?
Yes, sir.
Yeah. Similarly here, the function is 0 will imply integral is 0. But integral can be 0 without function being everywhere 0. Almost everywhere is enough. So g equal to 0 almost everywhere implies integral over g dm equal to 0. The converse is also true if the function is non-negative. If the integral is 0, the function will be 0 almost everywhere, provided the function is non-negative. Okay. Anyway, let me prove this first. If f equal to 0 almost everywhere, I have to prove that integral is 0. And now how do you define integral of f? Using integral of simple function. And phi is a simple function. Phi less than or equal to f, then phi will be 0 almost everywhere. Okay. And therefore, integral of phi dm, phi is simple function, will be equal to 0. So whatever simple function you take less than or equal to f, its integral is becoming 0. So if you take supremum also, integral will be 0. Therefore, integral of f dm will be equal to 0. Are you with me? Do you agree?
Yes.
How do you define integral of a non-negative function? Using integral of a simple function less than or equal to f. Today I told you, you can avoid this bounded business, etc. You can avoid level 1. You can directly go from level 0 to level 2. To define integral of a non-negative function, you take integral of a simple function less than or equal to it and then make it better and better. Okay. So this is straightforward. Now converse is bit involved. Suppose integral of g, I could have written g everywhere. G equal to 0 almost everywhere. G equal to 0 almost everywhere, and phi is a simple function such that phi is less than or equal to g. Phi is less than or equal to g, then phi equal to 0 almost everywhere. Then their integral will be 0. That follows from the definition. Because for simple function, it is summation of alpha I times measure of ei. Okay. Because of that, integral of phi dm will be 0. Once integral of phi dm is 0, integral of g dm will be 0. Now converse. Suppose integral over e g dm is 0. I have to prove that g equal to 0. To be precise, g equal to 0 almost everywhere. Okay. Let us consider En equal to, remember g is non-negative, set of all x such that g of x greater than or equal to 1 by n. Okay. Then integral of g dm is greater than or equal to integral over 1 by n chi en dm. Because of the definition of em. I don't want to explain too much on this. You can do it. This is 1 by n times measure of en. Think over it. Okay. With the definition of gn, see whether you can get it. And so, since integral of g dm is 0, you will get 1 by n times measure of en is equal to 0. And that will give you measure of en is 0. And now define E. E will be collection of all x such that, not E, because E is integral over which you are, no, set over which you are integrating. Collection of all x such that fx gx greater than 0 is equal to union of ens. If gx is greater than 0, gx will be greater than 1 by n for at least some n. So this is true. Set of all x such that gx greater than 0 will be countable unions of en. And each en is of measure 0. Okay. Therefore, collection of all x such that gx greater than 0 has measure 0. Each en is of measure 0 and some measure of union en will be less than or equal to summation measure of en as measure 0. So where it is positive has measure 0. That means g is 0 almost everywhere. G is greater than or equal to 0 and where it is greater than 0 is of measure 0. That means g is 0 almost everywhere. Okay. So we proved this result. A non-negative function is 0 almost everywhere if and only if its integral is 0. Okay. Now let us use this. Because f plus and f minus are non-negative and f plus and f minus are 0 almost everywhere, their integral will be 0. Since f plus comma f minus are non-negative and 0 almost everywhere by the above observation, integral over f plus dm would be equal to 0 and integral over f minus dm will be equal to 0. And that will give integral over f dm is equal to 0. Thus, if f equal to 0 almost everywhere, then integral of f dm equal to 0. We don't have converse. Integral f dm equal to 0 will not imply f equal to 0 almost everywhere. That is true only for non-negative function. The next proposition again, a simple property of Lebesgue integral. So first we proved linearity property, then we proved the fact that if a function is zero almost everywhere, then their integral is zero. Okay, try to get a counterexample for converse. That is, integral is zero, but function is not zero almost everywhere. Definitely you cannot work with non-negative function, because for non-negative function, integral zero will imply function is zero almost everywhere. Now next proposition again tells you a simple property of Lebesgue integral. First one was linearity. Second one was if the function is zero, integral is zero. Next, if again expected, f is less than or equal to g, then integral over f dm is less than or equal to integral over g dm. But I have to polish this. F less than or equal to g is not needed for all points in the domain. It is enough almost everywhere, as you all now can expect. Okay, the almost everywhere equal, the integral will not change. So if f is less than or equal to g almost everywhere, integral over f dm is less than or equal to integral over g dm. Proof is quite obvious from the previous proposition. We have to boil down, we have to convert it into the case where f equal to 0 almost everywhere. So what you do is write g is equal to f plus g minus f. F plus g minus f. Okay. Therefore, integral over g dm, by the linearity we proved, integral over f dm plus integral over g minus f dm. Okay. Now, what can you say about g minus f is that it is greater than or equal to 0 almost everywhere. So let us not use that. I will decompose this g minus f into 2. This is equal to integral over f dm plus integral over g minus f dm by definition is g minus f plus dm minus integral over g minus f minus dm. Okay. Now what you know is f is less than or equal to g almost everywhere. So what can you say about f? G minus f minus. By definition, this is, what's the definition of g minus f minus? Maximum of
minus g minus f.
0, comma
Minus of g minus
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 g
g.
minus f of x. Okay. Now you know that g is greater than or equal to f almost everywhere. Okay. So this maximum will be 0 almost everywhere. Right. Therefore, g minus f minus is equal to 0 almost everywhere. Do you agree?
Yes, sir.
Yes, sir.
And once a non-negative function is 0 almost everywhere, its integral will be 0. Therefore, integral g minus f minus dm is equal to 0. Okay. And therefore, integral g dm is equal to integral f dm plus third summand will not contribute anything, plus integral g minus f plus dm. Now can you conclude the result? Integral g dm is
Yes, sir.
integral f dm plus something, and that something is non-negative. Why? Because g minus f plus is non-negative. Okay, and therefore integral over g dm is greater than or equal to integral over f dm. So if g is greater than or equal to f almost everywhere, integral of g is greater than or equal to integral of f. Not almost everywhere. There is no question of almost everywhere for integral. Integral is a number. So this number is greater than or equal to that number. Okay. Next proposition. Again, a familiar or an expected property, which you call as domain decomposition property. If A and B are disjoint measurable sets, integral over A f dm plus integral over B f dm will be equal to integral over A union B f dm. Instead of integrating over the entire domain, you can divide the domain into disjoint subsets and then you can integrate. Okay. Proof. These are all some obvious property that we expect for any integral. Linearity, monotonicity, f less than or equal to g should imply integral f less than or equal to integral g. But in the Lebesgue sense, almost everywhere is enough. And now you can decompose the domain into several subdomains. Again, the proof is simple. Integral of A union B f dm. How do you define integral over A union B? How do you define integral over E? One thing, as I told you, you can always stick to integral over R. There is no need to do integral over E. Always you define integral over R. And then if you want integral over E, use the characteristic function. So maybe you can write this as chi A union B f dm. Okay. But I have listed a property of indicator function. When A and B are disjoint, chi of A union B is chi A plus chi B. That is easy to verify. F dm. That's it. Now f is linear and all. You can, not f is linear. Integral is linear. So integral of chi a f plus chi a b, chi b f. Here we don't need linearity. We just apply the definition of the product. Now apply the linearity of the integral. This is integral of chi a f dm plus integral of chi b f dm. Here we are applying linearity, which we already proved. And this is integral over a f dm plus integral over b f dm. Okay. Now let me make an important but easy observation. This we shall use. Suppose f equal to g almost everywhere. We have f equal to g almost everywhere. Then you can see that integral over f dm will be equal to integral over g dm. Everything boils down to simple function. In the simple function, definition is alpha I times measure of ei. So if measure of something is 0, that will not contribute anything for the integral. Because of that reason, whenever you have two functions almost everywhere, then integral of f dm is equal to integral over g dm. Okay, keep this in mind. So integral will be unaltered when you have two functions. One varies over the is different from the other only on a set of measure 0. Now I think I will stop the business of simple properties of integration here, and what is to be highlighted is how this Lebesgue integration is superior to Riemann integration. For that, you have to recall the drawback or the shortcoming of Riemann integration, namely that Riemann integration is not well behaved with respect to the limits. It is not stable with respect to the limit. If each fn is Riemann integrable and fn converges to f, we cannot say f will be Riemann integrable. Even if f is Riemann integrable, integral of f may not be equal to integral of fn. We need to ask those type of questions for Lebesgue integral. Okay. So the next main question, at least I will write the question so that this will be the starting point for our next lecture. Next main question is this. Suppose fn is a sequence of Lebesgue integrable functions. Lebesgue integrable functions. To talk about Lebesgue integrability, at least we should start with measurable functions. So obviously, Fn is a sequence of measurable functions. And let Fn converges to F almost everywhere. Fnx converges to f of x almost everywhere. Okay. Then is f Lebesgue integrable? That is one question we want to ask. One. And second question is, suppose it is Lebesgue integrable. Now you can talk about integral f dm. Is it same as limit n tending to infinity integral fn dm? Because f is limit fn, this is limit fn almost everywhere. And you know, as far as Lebesgue integral is concerned, whenever f equal to g almost everywhere, integral f is equal to integral g. So we don't want to deal with fnx converges to fx for all x point-wise. It is enough to have almost everywhere. The question is whether the limit function is integrable. If it is integrable, whether integral of the limit is same as limit of the integral. This is the question what we asked in Riemann, and we have seen that in Riemann this is not true. Okay, and that is the reason why we went for some other kind of integral, for instance Lebesgue integral. So obviously we should expect that Lebesgue integral satisfies these conditions. Okay, but unfortunately, let me give an example and stop. On 0, 1, let me define a sequence of functions. Fn of x is equal to, let me copy down, 1 by x characteristic function on 1 by n 1. This is how I define Fnx for each x in 0, 1 and n is equal to 1, 2, 3, etc. Okay, and let me define another sequence Gn. Gnx is equal to n times chi 0, 1 by n of x. I am going to make some claims about this and I will leave it as an exercise and stop the class. So Fn, each Fn, then each Fn is Lebesgue integrable. Please see. Please try to see that they are all Lebesgue integrable. Fn converges to f where Fnx converges to fx. Point-wise convergence only I mean, where f of x is equal to, you can guess, as n tending to infinity, this chi will become 1 by n 1, this will become 0. So this will be on the entire 0, 1. It will be 1 by x when x is greater than 0 and it is 0 when x is equal to 0. Okay. But f is not Lebesgue integrable. So you have to convince yourself that each Fn is Lebesgue integrable and you have to convince that the limit function is not Lebesgue integrable. So we are in a similar situation like Riemann. Okay. Next, let us consider Gn. Okay. Gnx converges to where it will converge. Can you guess? As n tending to infinity, what happens?
0.
0.
0 function. Gnx converges to g of x, where g of x is equal to 0. And integral of Gn, I will take these examples once again in the next class. This is going to be our starting point in the next class. Integral Gn dm not dx, dm. Gn is n times, so n times, then you will get the measure of this, that is 1 by n. So integral gn will be 1. Integral gn is 1, but integral g is 0. Integral g dm is 0. So the first example tells you that fn converges to f. Each fn is Lebesgue integrable, but the limit function is not Lebesgue integrable. And second example tells you that each gn is Lebesgue integrable. The limit function is also Lebesgue integrable. However, integral of the limit is not same as the limit of the integral. Okay. So the questions that we ask is in negative. Answer is negative for both the questions. Okay. However, with a mild conditions that you impose on fn's, possibly on f and so on, you will see that these questions have a positive answer. And that's what we are going to discuss next through a series of theorems, at least 4 theorems. 1. Bounded convergence theorem. 2. Fatu's lemma. 3. Monotone convergence theorem. And these theorems are fundamental building blocks of entire integration theory, Lebesgue integration theory. And one more, bounded, Fatu's, monotone, and Lebesgue dominated convergence theorem. Dominated convergence theorem. Okay. So these are all different theorem, but addresses the same question. Namely, if each fn is Lebesgue integrable and fn converges to f almost everywhere point-wise, is it necessary that f is Lebesgue integrable, and whether integral of f will coincide with limit of integral of fn? Okay, all these 4 theorems discusses that. Okay. You can guess from the name. As I told, with the general fn and f, you don't have an yes answer to this question. So you have to impose certain conditions. And what are the conditions imposed will be clear from the name. Bounded convergence theorem. Can you guess roughly what may be the conditions? Bounded convergence theorem. Each fn is
bounded.
Roughly, okay. Forget about Fatu's lemma. Next, monotone convergence theorem. What could be the condition, hypothesis? This fn sequence that you are taking is a
Monotone
monotone sequence.
Sequence.
Fn less than or equal to fn plus 1. Okay. In that case, roughly what you can say is that integral of fn will converge to integral of f. Okay. And what can be the dominated convergence theorem? The word dominated tells you that suppose your fn's are such that modulus of fn is less than or equal to some function g. There is a function which dominates all these fn, and suppose that this g is Lebesgue integrable. Okay, modulus of fn is less than or equal to g, and this g is Lebesgue integrable. Then if fn converges to f, the integral of fn will converge to integral of f. So your sequence is such that it is dominated by an integrable function, that is dominated. And Fatu's lemma says what best we can say in case there is no other assumptions like monotone, bounded, dominated, nothing is there. Then what best we can say? We cannot say talk about limit. Limit may not even exist, but we can talk about limit infimum. Okay, so the Fatu's lemma will be something connected with limit infimum of fn's. Okay. So I have given you an overall picture of what we are going to do next, maybe 1 or 2 class to maybe needed to explain all these convergence theorem. So the basic question is this: If each Fn is Lebesgue integrable and Fn converges to F point-wise, is it necessary that F is Lebesgue integrable? And is it necessary that integral and limit can be interchanged? In other words, whether Lebesgue integration is stable with respect to point-wise limit. Answer is no, but you can put mild conditions. Okay. And depending upon what condition you are imposing, you have different theorems. Okay. That this is going to be one of the crucial part of this course. Okay. And in fact, the course ends with this almost. The rest of the thing is only some adding more flavor to it. That's it. So the main part is definition of Lebesgue integral and the properties of Lebesgue integrable through these four convergence theorem. That's it. That's the main content of this course. Yeah. With that, let me stop.